In last lecture, we started discussing continuum. The concept of continuum is valid when matter can be related, when matter can be treated as continuously distributed without any void being present. So that is when mean free path of the molecules is very less than system dimension. Okay. For this, we can consider it in this way. Like let's consider system. In this system, we have considered a point P, and around the point P we have considered a very small region having volume delta V and mass delta M. Okay, so here we will what we will do, we will start to shrink this volume size. Okay, so we will plot a graph. So let's say we are plotting it between delta V, volume, and density, dm by delta m by delta V. Okay, so so if the volume for this, let's say for this particular volume, the average density is rho. Okay, so let's say this is the average density, and this density value is rho. Okay, and at some volume, at some critical volume, like so after this some particular volume, let's say is delta V dash, uh, if we shrink the volume less than delta V dash, what will happen, that the average density fluctuate, average density will fluctuate, and it occurs due to very random motion of the molecules in and out of the considered control volume. Okay, so from this control volume, the molecules will rapidly, some molecules will come out, some molecules will come in, and due to this rapid motion, the particular value of density cannot be determined. Okay, so this density value can either decrease or else it can increase. Okay, let me. Okay, so this reason uh, describes the domain of molecular effect. Okay, and similarly this reason indicates the domain of continuum. Okay, so this domain is applicable for our microscopy study, which further can be used in domain of continuum, and this the domain of molecular effect is effective for the study with microscopic approach. Okay, so this suffice our continuum. Okay, the one more thing, mean free path. What is mean free path? Okay, so let's consider a system volume. So this is a system, let's say, and there are two, let's say there are molecules. Let's consider these two molecules for a moment. Okay, so what is mean free path tells us is the average of distance between two successive collisions of molecules. Okay, so let's say they both molecules move toward each other. Okay, and at certain point they both collide. Okay, so here they both collided. Okay, so this this distance is called free path. Okay, so free path distance. So average of all such distances will be called mean free path. Okay, so let's say here that this is system dimension, let's say L. Okay, and mean free path, let's say the mean free path is generally indicated by lambda. So let's say lambda is uh, greater than L. What would it mean? It would mean that the mean free path will be greater than system dimension. So when that happens, then the molecules will frequently move in and out of the system. Okay, and we will entering the domain of molecular effect here. So, for this system study, if we have to use the concept continuum, then we have to stay in the domain of continuum. Hence, for that, the lambda mean free path must be very less than system dimension that I mentioned here. Okay. Next, uh, okay, one more thing here, that there are some questions asked about rarefied gas theory. Okay, so gas theory, gas flow theory, sorry. So generally in space applications, let's say that a satellite or is orbiting around around Earth. So what happened that in space the density of air is very less, very low. So at randomly some molecules will strike on the like space station or the satellite, or there are many particles in the space, many freely moving particles that will strike. So to study this type of flows, we use rarefied gas theory. So rarefied gas theory is basically used in microscopic condition. You should know this much only. I mean, microscopic conditions. Okay. So I mean, this won't be much useful to us currently. And for further details, you can Google it or read in some book if you fancy this topic. Next, we will be moving to pure substances. Okay. So next is pure substances. Okay, so what is pure substance? So a substance is said to be a pure substance if if it is homogeneous, it is of homogeneous chemical composition throughout. Chemical composition throughout. Okay, so we will see some examples. So let's talk about the first example. First example is gaseous mixture of O2 and N2. Okay, and so while studying this, let's consider system. Okay, so this is a system and there are many oxygen molecules. Let's say these are oxygen molecules. Okay, so these are oxygen molecules, and let's say there are nitrogen molecules also. These are N2 molecules. What we will do here, we will consider various sections. Let's say this is the first sample, this is second sample, this is third sample. So if we like say both are in gaseous phase, they will mix perfectly. Okay, let's say so what will happen if we pick up any of these samples, we will obtain same percentage of, like, let's say if there are 50% of oxygen and 50% of nitrogen in the system. So in each and every sample there will be 50% of oxygen and 50% of nitrogen. Since this is the case, this will be a pure substance. Okay, pure substance. So mixture, gaseous mixture of O2 and N2 is a pure substance. Let's take in second example, mixture of water vapor and water. Okay, so here also we will consider system, and similarly let's say that there is water. So here it is, let's say a water. Okay, and these are water vapors. This H2 vapor. Now if we consider any sample, like let's say this is sample 1, this is sample 2, and this is sample 3. In all three samples, what we can see has 100% water. Okay, so all have so everywhere it has same chemical composition, so it is also a pure substance. Let's move to the third example. So third example is a mixture of water plus mustard oil. So here we will also make a system. So let's say this is a system, and here this section will contain water, and this section will contain, let's say, mustard oil. Let's take three samples, sample 1, sample 2, sample 3, and here we can see that this is a not a pure substance. Why? Because in each and every sample the chemical composition is different. Okay, so let's take one more example. Let's take the example liquid air plus gaseous air. Okay, so let's take a system. This is a system. Okay, and here is our gaseous air, and here is it our liquid air. Here it is gaseous air. So here we will also take few samples. Let's say this is sample 1, this is sample 2, and this is sample 3. So we can see that in all these three samples, so for liquid the composition of air is different. Okay, so there is 12.5% O2 in liquid form if we talk about air, and in gaseous form there is 65% of O2. Okay, this occurs due to the freezing temperature of different gases are different. Like in air, there is oxygen, nitrogen, carbon dioxide, and for all these, the liquefaction temperature is different. Okay, so since it is different in liquid air, the percentage of O2 and O2 it will be different from that of in gaseous air. Okay, so if we all check all three samples, we will get that this is not a pure substance due to the chemical composition difference. Okay. D- Next, we can move to a very important topics, that is Gibbs phase rule. Gibbs phase rule. Okay, so Gibbs phase rule. Uh, so this rule state that, so this is the formula which we have to remember first. P plus F is equal to C plus 2. Here P is, let's state this term first. P is number of phases. So number of phases you will count solid, liquid or gas. ठीक है. Next, F is degree of freedom, and C is number of chemical components. Okay, so here one more thing here to represent the two basic thermodynamic temperature properties. So to define a state of the system in thermodynamics, we use, let's say, pressure and temperature, or temperature and volume. So any two properties. Hence, for thermodynamics, this coefficient is 2. And if we talk about material science, in material science, generally the pressure we work at is atmospheric only. So there is only one variable which represents the state of the material, that is temperature. Okay. So in material science, the formula begin P plus F is equal to C plus 1. Okay. So the thing is here, what is degree of freedom? So let's talk about degree of freedom. Degree of freedom. So degree of freedom is minimum number of independent intensive properties, intensive properties or variables required to fix the state of the system. Okay, so we will look at some examples. So let's say example number first is water plus water vapor. Water plus water vapor. Okay, so if we apply P plus F is equal to C plus 2. Okay, so let's see how many phases are there. There are two phases, that is water and gaseous. Plus degree of freedom we have to calculate is equal to C. How many components are there? The component is only one, that is H2O in both cases. Okay, plus 2. So we'll get is equal, F is equal to 1. Hence, the degree of freedom required to represent water plus water vapor is only 1. Okay, so that is from one variable we can specify the state of this system. Okay, so let's talk about the second system. Second system is O2 plus N2. Both are in, like, let's say, gaseous. Okay, gaseous. So if we apply the same thing, P plus F is equal to C plus 2. So here the number of phases, all in gaseous phase, plus we have to calculate degree of freedom, is equal components O2 and N2, two components, plus 2. F is equal to 3. Minimum 3 intensive properties are required to fix this state. Okay, let's say the third example, triple point of water. Triple point of water. Okay, so one thing you have to remember, like you can either remember or just keep it in mind that the critical the pressure at triple point is 0.61 kilopascal, and temperature is 0.01 degree Celsius. Okay, so we will apply P plus F is equal to C plus 2. F is equal to C plus 2. We can take phases, number of phases. There are 3 phases, plus F is equal to C, number of components. There is only one component, that is water, plus 2. So F is equal to 0. So in case of triple point of water, no property is required to specify it. Okay, it is self sufficient. Okay, so we can move to next topic.